Okay, all right. Um, so let's start talking about CMOS inverters. Okay. So when we talk about CMOS, right? So yesterday we talked about um, what is CMOS and what are the different families and all of that. Now, when we say CMOS, what is the basic circuit that we usually start with? So it is always the inverter that we actually start. Okay. So now this is a kind of say PMOS, and say this is kind of NMOS, and this is how we actually get started. So now yesterday we have seen that this is something we call it pull up network, and then this is something pull down network. Okay. Now why we keep PMOS on the top?
Strong one.
Okay. So that gives a kind of strong one always. Okay. Now we as I said, right, for digital circuits we always prefer strong one and strong zero. Okay. Now so we kind of say constructed, it's kind of the PMOS on the top, NMOS at the bottom. Okay, so PMOS gives you strong one and NMOS gives you strong zero, and this is basically work, this circuit is going to operate as a inverter. Now what would happen if you interchange this PMOS and an NMOS? What would happen if you interchange this PMOS and an NMOS? And I asked you guys to complete this assignment, right? So how do you design a buffer?
So sorry, if we interchange, we will get that weak buffer.
Okay. So when you interchange this PMOS and an NMOS, so that means your pull-up network, it becomes like kind of NMOS, and your pull down will become PMOS. So now this is going to give you say week one, and this is going to give you say a week zero, which we don't prefer. And also the circuit would operate, or the function of the circuit is going to be, we call it like kind of say buffer. Okay. So we don't prefer that. As I said, the digital circuits we always prefer strong zero and strong one. Okay. Okay. All right. Now, so how does this inverter operates? How does this inverter operates?
So basically, sir, with the zero input, the PMOS get activated and the load capacitor charges from the PMOS. At the same
Okay.
time, the NMOS would be open circuit. And when the inputs change, then the NMOS got activated and the supply get disconnected from the PMOS pull-up network. At that time, the load capacitor get discharged by the NMOS to the ground. So when we applied zero, we get one at the output and vice versa in the other case.
Okay. So when you give zero here, so your PMOS turns on and it charges your capacitance. So now that, when you say charging this capacitance, so you need to understand that this load cap. So is it possible for you to avoid this load cap? So we say always, there is a cap or load or whatever it is, but is it possible for you to avoid this load cap? What is this load cap? Okay, a simple thing. So yesterday we have seen the CMOS cross sectional things, right? So now you have this is actually what. So we have discussed it like kind of say this kind of cross section. So now this is P substrate. This is your metal. And what about this one?
Oxide. Oxide.
So it is oxide. It is basically SiO2, silicon dioxide, right? Now this is actually treated, or this is kind of treated as a pin capacitance. So that is treated as a pin capacitance. Now when we say this C load, what is this meaning is say C pin and then plus C net. So what is this meaning is, so just look at this way. Say this is your inverter is driving say a fan out of say 10. Okay. Now this is your 10 fan out, and this also called as a say net TA. Okay. Now what is the C pin? What is the C pin?
So basically, the semiconductor cap across the drain of PMOS and NMOS.
So it is basically the cap of gate cap. It's a pin capacitance.
Okay.
Okay. This is the pin capacitance that would you would be able to charge. Okay, so now this is the terminal that would be charged to say VDD or VSS or 1 or 0 and etc. Okay, now your pin capacitance is basically depends on your the number of fan outs. Okay, and then you have got net A, which is kind of driving this output and connecting all this inputs. Okay, so now this is something that we call it as a net. Okay, now that net will have its capacitance. Okay, now that is your net capacitance. So this depends on your basically your routing. Okay, not at this moment, but when you get into the physical design stages, something called routing, then your the net capacitance also comes into picture. So now when you say the load capacitance, it is impossible for you to get rid of it. Okay, it is impossible for you to get rid of it. So you have to live with that. Now ideally, when you give 0, now what will happen to say assuming this particular thing is connected to, so this Z is connecting to this metal, this gate. Okay, now what is this meaning? What is this meaning? What is this meaning?
Z is
Okay.
charging the metal gate.
Exactly. So this is charging your gate supply voltage is going to be the when it's basically going to charge up to say VDD. Okay, that is the main thing. Now during this whole thing, you're charging. When we say a charging of load cap, the load cap is nothing but your the next stage pin cap plus your net cap. Okay, so these two are an important thing. Okay, now you should always remember because this is going to play a crucial role when it comes to power and when it comes to performance and all of that. Okay, now so we were talking about when A is 0, your PMOS is on, and this PMOS is charging this load cap. So this load cap charging meaning what? It is basically pulling this gate level, the gate potential to VDD. Okay. Now, so the node Z is charged up to VDD. That's basically logic 1. Okay. And when A is 1, okay, now that cap whatever the charges. Okay, it is kind of discharged. Okay, it is kind of discharged. Now NMOS is on, okay, and PMOS is kind of not on. So we talked about it, right? And then your Z, the node Z is kind of discharged all the way, completely gets discharged to VS, to the level zero, the ground level. And then, so it is going to be, we call it like kind of logic zero. Now when this happens, your gate, okay, when this happens, so your gate is basically at ground potential. Okay, this gate is at ground potential. So that is how your circuit basically operates, and the next stages or gets charged, meaning it is kind of, see, it's kind of charging, meaning the gate value, the pin over here, it is something we call it like kind of pulled up to the logic 1. And again, if it is kind of pulled down, it's kind of when it gets discharged, it would become kind of logic 0. Okay, so this is the kind of basic understanding that you should have. Then you are very good in your device level understanding. Okay, is that clear? Anyone has any kind of question, you can raise your hand or unmute and ask. Okay, moving on. Now, so how do we design the buffer now? How do we design a buffer now?
Cascading to inverters.
Exactly.
Okay.
So it is basically, now you take this kind of thing. Now, okay, so I think, so basically you need to put it like this. Say this Z is kind of driving this A. Now this is your first level inverter. Okay, so now this is kind of, say, buffer. So it is basically how it is going to be is kind of, say, you have a first inverter, and then you have another inverter. Okay, now your first level is basically the inverter, and then again the second level is again another inverter. Okay, so this is how you have to design a buffer. Now remember, usually when we design a buffer, okay, so yesterday I was asking you guys, or probably I gave a homework, what is the meaning of drive strength? What is the meaning of drive strength? What is the meaning of drive strength?
So, sir, it would be the C. I mean, the total cap it can handle at the output, like number of gates
uh
that can be connected to the gate.
okay, so now what is it meaning is drive strength, meaning yesterday we were talking about, say you have W and L, any transistor that you take. Say for example, so we were talking about something called W by L, and say W by L. Okay, now so this W value, or say I would say This is say kind of 2W, and say this is 1W by L. Now assuming say this is inverter X1, okay, and say HVT type, okay, that is kind of say HVT type. Now the same thing, what we do is you want to have a bigger driving capacity, okay. Now what we do is, say for example, now this is 3W by L. Now this is 1.5W by L. Okay. Now this is going to be say kind of inverter X4 underscore HVT. I'm just giving you some rough thing, or say take this as a kind of X2. So X2, and then this is X4. Now this is going to be inverter X8 underscore HVT, for example. Now, so you might say 4W by L, and this is kind of 2W by L. So, so when you say your drive strength increases, okay. Now, what does this meaning is, that means your W increases when your the drive strength increases. What is that meaning is your W, the transistor W, both NMOS and PMOS increases. So that means the tool, I mean, basically that this transistor or this whole gate can drive more load. Okay, this can drive more load. Okay, is that clear? So now, why do we need different drive strengths? Why do we need multiple drive strengths? Why do we
In the
need?
design, there may be
Go ahead.
so in the design there may be many situations to drive more length or more gate caps. That time more strength will help.
Okay. So remember, there may be a circuit, okay. Say for example, now say you have an inverter, which is kind of say X2, okay, say X2. Now this might drive say kind of 4 fan out, okay. Now there may be a drive strength that you may need to use. Say for example, you have a 15 fan outs, so this may be kind of say X8, okay. And again, you may have bigger, more number of fan out. Say for example, you may have a 24 fan out, then you might need say X16 kind of thing to drive all these things, okay. So you definitely need different drive strengths, so that you can actually size the cell depending on its load, okay. You can just size the cell depending on its load. Okay, so now getting back to your buffer. Okay, so we were talking about buffer. Now, say the way I look at, right? So it is going to be kind of say inverter, back to back inverter. Remember, the first stage is going to be a smaller inverter, and the second stage is going to be a bigger inverter. Now, why are we doing this? Now, if you look at this is kind of a buffer. So on the top, if you look at it, is kind of buffer. Whereas internally, if you look at this, both of them are, say, inverter X2. Say this could be inverter X8. Okay, so why are we doing this? Any idea? Why are we doing this? Any idea?
So
Sorry, was there someone talking?
Generally, we use a buffer in a long net, like a long path of the signal. So the signal might be weakened. So in order to amplify the signal, we use a buffer.
No, no, I'm
So
asking, I
that's
mean,
the
I'm not
reason
asking you,
you take
I'm not asking what is the use of
that.
buffer. I'm asking why do we need,
No,
why are we going for two stages?
so the
Okay, two
second
stages is
stage
fine, but
is a higher drive.
go ahead, Rashmi. Sorry, I was stopped.
So the second stage will be a higher drive source. So it is actually amplifying the signal.
Okay, so in this case, right now, if you guys look at what this is exactly is, so we just talked about it, no? Now this inverter load pin cap is going to go, assume, say there is a NAND gate which is kind of driving this buffer. Now this inverter pin cap is going to contribute as a load cap. Okay, so we want usually, uh, the cap, the pin cap should be less, so that, the first stage cap should be less so that your load cap can be lesser. Now the next thing, but that is fine. So you're taking care of, the first stage being small is to take care of your load cap, the previous stage, the load of the previous stage. Okay. Now the second stage, you having a bigger, drive, or say bigger cell or bigger W, is to drive this bigger load. Okay, to drive a bigger load. So that way you're kind of taking care of two things. You are not increasing your previous stage load cap, and also you are actually kind of taking care of your longer, or say you can say, you can say the cell is capable of driving a bigger load as well. Okay, so is that clear for everyone?
so maybe next level, but while designing the buffer uh, between the two inverters within the buffer,
Okay.
uh, the tran is how the transition is maintained. It is as part of design of buffer, right?
No, it is very short, no. So there is nothing that, again, this will be taken care internally by their simulation and etc. when they are designing the cell.
Right. Okay. Yeah.
So they would take care. See, it is literally there is a zero net, no. The net length would be just, so we'll talk about the layout part. So at that time I'll explain
Sure.
you. Now, this net length could be literally, say it is going to be very small. So the RNC of this net is going to be much smaller because you're designing the cell and doing the layout and exactly, which is sitting next, just next to each other. See, this
Yeah.
is something that nobody is going to ask you why this level in interviews, but you knowing this is going to add more value. You would be able to, talk in a much more confident way. Now, can I ask you guys on a simple thing? Now, what are the different cells that you can think of having some kind of two stages like this? Can you think of some cells which you might feel that okay, I needed two stages, something like this? The first stage can be smaller, and second stage can be a bigger, and etc. Any cells that you can think of?
So transmission time, when we send the signal to the receiver end, so that time the final driver should be a bigger strength, but the previous stage should be lower strength.
Yeah, right. I'm just trying to understand what are the different cells that you can think of. Something like this. Say buffer is one such example. Okay. And so normally in a digital world, how the cells would be. So what are the different cells, the basic gates that you are aware of?
So you mean the stages? I mean two stage cells like AND or
Yeah, right. Something
basic
like
NAT.
this. Correct.
Okay.
AOI and OAI cells also.
Yeah, I'm going to do this mux as well. So just write down this, and I want you to figure out what are all the cells that are going to be two stage cells. Okay, so there are some things like this. Okay, now first you guys have to understand that your load cap is basically nothing but your C pin. I'm just repeating the whole thing because someone was asking in the chat. So your load cap is nothing but your C pin, your fan out pin capacitance, and then your net capacitance. Collectively, are putting both of them together. It's kind of forms as a load cap. Now, so when what is the disadvantage if you have a higher load cap? Is it advantage or disadvantage? You having a higher load cap.
Disadvantage.
Uh, how?
So the previous stage has to be comparatively bigger to drive it, and that way the series,
Okay, so is that is the only thing?
the power consumption.
Uh, how power consumption is something in the signal?
So the bigger the width, the power it will take more to drive.
Yesterday I covered it in detail. I'm not sure how many of you remember it. So, is there anyone who can answer this part? So, I
Signal
need
different.
more precise answer. So, yesterday we were talking about power. So watt power. So you are no more on normal, just a plain textbook. You are gone through the class yesterday, and we have talked about it along with this equations and where the C load cap comes into picture, in which power.
Short circuit power, sir.
Uh, are you
Switching
sure?
power.
Short circuit power, there is no way. So we say switching power.
Switching power.
So switching power, the formula is basically alpha C V squared F. This C is nothing but your load cap. Okay. So when we design any kind of standard cells, if it is a single stage, you don't have any other option. Okay, you cannot do anything. But when you identify two stage cells, then you can try to bring down the first stage gate capacitance, that is nothing but your pin capacitance, so that your previous stage loading, or basically you can say cap, would become kind of lesser. That would actually help your overall, power, performance, and etc. Okay. Now remember, if you so in terms of power, so this is P switching. Okay. Now your power is going to go up. Now when you have a bigger cap, so what will happen to your delay of this cell? Say a simple thing. Let me ask you. Say this is your water tank. Okay. Now say you have got a tap. Okay. Now you keep a small bucket. Now how much time does it take to get the fill this bucket? Okay. So there is a example. Like say you have a small bucket that you are keeping. Now you are just turning on this whole switch. Now how much time does it take to fill this bucket? Assuming X. Okay. Now you are actually keeping a bigger bucket. Now how much time does it take to fill? So will that be same?
Yeah.
So
No, sir.
now you're remember, I'm yet to cover something called dot lib. Okay, we would be talking about this in the upcoming classes, where your delay depends on your input tran. I will talk about this. Okay, and output cap. Okay, so your cell delay is a function of input tran and output cap, that I will talk about it in the upcoming class. Okay, so please hold on to it. Now, you having a bigger cap is going to have increase the cell delay. So it is going to harm. So when you have your cap, which is on the higher side, you will have both power and performance getting degraded. So that is the main reason when you have an option to, or when the circuit designers or the standard cell designers, so they always look to target your the first stage cap is kind of lesser, and then they actually, the second stage would be the best one to drive the long, bigger load kind of thing. Okay. All right. uh, So this is your kind of homework. I want you to work on it and let me know what are all the cells that is going to be kind of, different, single stage cells and then multiple stage cells and etc. So at least I want you to have 10 different cells. Okay, 10 different cells. So you can add half adder, you can add full adder and all of that. Okay. Okay, all right. So now we were talking about buffers and everything. Now, so let's get back to inverter. Now, when someone asks you to explain your inverter, okay, now, so I always look at you actually doing, drawing this schematic and then say the symbol and explain how the schematic operates and everything. Now remember, there is always something called voltage characteristics. Okay, there is something called voltage characteristics. So that would always come into picture. So what is it called? So have you heard about something called a VTC? What is it? What is it called? So if you guys look at your inverters, say it is going to be always something like this. We actually plot it. So people call it VTC or inverter characteristics. Okay. Now what is this? Remember, we always give V in, as an input, and your input is always on the x-axis and your output is always on the y-axis. So that is kind of V out. Okay. Now if you look at when your input is kind of zero, okay, now your output is kind of going to be on the higher side. Okay. Now if you ask me this, say this is zero, say this is say 5 volt for example. Okay. Now say this is going to be kind of 5 volt. Now this when you say inverter is the input is zero, that means your output is going to be kind of charged up to VDD, which is of 5 volt here. Now when your input becomes zero, your output is going to be at zero. Sorry, in your when your input becomes higher, that is basically a 5 volt. Okay, now your V out eventually becomes a zero. Okay, so this is something that it is important when it comes to your inverter characteristics. So if someone is asking you to explain inverter in detail, so always go and do this way. So see basically how you construct an inverter. Basically say what is the inverter and truth table of inverter, and then how do you construct the schematic. Okay, and then explain how it is actually operates, and then finish it with your VTC curve. That is the way I would actually do that, or I would explain this way in the interviews. Questions here, any? Okay, okay. Now, so let's draw a NAND gate. So the first thing that you guys have to understand this particular thing. Okay, this slide. Now remember, so this whole thing it is say PMOS, and this whole thing is kind of say NMOS. Okay. Now, say if you have one MOS in the bottom, that is NMOS, and you have to have a PMOS, which is of similar type with the A kind of, going to the input. Now, this is going to be conducting, both A and B is going to conduct only if both of them are 1. So it is basically and conducts if both A equal to 1 and B equal to 1. Now, the same circuit when it comes to PMOS side, it is basically exactly opposite. So anything parallel here becomes a anything serial here, series here, now becomes a parallel here. Okay. Now, so in this case, if both of them are kind of in parallel, if any one of is one, it's still going to conduct. Now, the parallel transistors at the NMOS, which is in the pull down, now becomes a series at the top. Okay. Now remember this, and then we will go and do the implementation for the NAND gate. Okay. So let me ask you a simple question. So is NAND gate or AND gate? So basically, which is bigger in terms of area? Which is bigger in terms of area?
And gate, sir.
AND gate.
Okay. So A and D. So only two people, um, said AND, I believe.
AND gate, sir.
Okay. So total three. Then what about others? I see more than 20 people.
And it.
Okay, AND gate. Okay, so four.
NAND gates.
Okay, so NAND got one answer finally, one voting. Okay. See, remember in your
And
digital,
get
so we always have AND gate and then we add one inverter. Okay. Now think if you want to change your answer. Now this is what NAND gate, no? Correct. So which is gonna be more area?
NAND gate, sir.
NAND gate is bigger. Okay, so there is one more answer. What about others?
Na- NAND gate, sir.
Okay, NAND,
NAND gate.
NAND, okay, okay, NAND. Okay, so I see 4 plus 4, and what about others?
and get
Okay, so this guy is getting one more. Okay, one.
NAND gate.
Huh?
NAND gate.
Okay, so equal it is going.
NAND gate, sir.
NAND gate. Okay, so there is a one more. Okay, so we will see it in a while. Okay, so just keep this aside by. We will revert back. We will design the gate and then we will look at the area. Okay, so that you get to know whatever the answer, whether you have given is right or wrong. Okay, so what is the formula of, what is the Boolean equation of NAND gate?
A
A
dot B bar.
Okay, so it is Z equal to A.
A B whole bar.
Okay, so AB
AB
whole
whole
bar.
bar.
Okay, now remember the way I used to tell people, this is how I draw the circuit. Now take only this AB, leave this bar as it is. Okay, just take only AB and leave the first, only, bar as it is. Now what is this AB meaning? A dot B. What is this meaning? A dot B meaning?
AND gate.
And
So it is going to be kind of say AND gate. Now if it is AND gate, which one will you pick among this?
Middle one.
Sorry.
Middle one.
Okay, so
series of
basically now remember you need to just draw it like this. So this is going to be your full, kind of say the middle line. Now you are going to draw this way. So this is going to be your A and this is going to be your B. Okay. Now, what did I tell you guys? Whatever is there in the bottom, right? Whatever is the the circuit that is there in the bottom, now that becomes parallel. Okay, that becomes parallel, and say this becomes A and this becomes B. Okay. Now, say this is going to be your Z. Now, what is this meaning? So for inverter, right? What did we do? CMOS by default has the inverting capability. Okay, so Z equal to what? I bar. Now, what did we do? Only this I, we have just picked it up, and then the opposites of that is kind of NMOS, of the PMOS, and we have just connected it. Now, let's analyze this. So, what is the truth table? Can someone tell me?
0110
1011.
11.
No. Okay, so
Zero.
I, what is the value here? It is
One
1.
one
Mm.
one
One.
one
Zero.
zero zero zero.
Okay. Okay. Now, so this is your truth table. Now, so you believe that you have drawn the circuit. Now you need to verify that with this particular truth table. Okay. Now, how do we do this? Can we start applying zeros and ones to all this and see? So now apply A, and A is equal to 0 and B is equal to 0. Now what actually happens when A is equal to 0? What happened? So this is P1, this is P2, this is N1, this is N2. Now in this case, what actually happens? What happened to your P1?
On
on,
So your P1, P2, N1,
both are
N2, and Z. Okay. Now your P1 is on. Your P2, what about your
on
P2?
on,
Okay.
on
And what about your
on,
N1?
off
off,
Why it is off?
8
zero,
0
is
NMOS
Okay. And what about N2?
Off.
off,
off.
Okay. Now what is going to be your output?
one,
VDD
So now your both the transistors are on, both the PMOS are on. Now what is this meaning is it is going to be kind of logic one. It is because it is charging. Okay. And there is no discharge path. Only charging path exists. Okay. Is that clear? Now let's talk about the next set. So can you guys tell me what it is going to be?
P1 on,
P1 on, sir. P2
Okay.
off.
Okay.
N1 off. N2 on.
Okay. So P1 is
N1
on
on,
and P2 is off and N1
off,
is
Off.
off
off,
and
N2 is
N,
on.
on,
N2 is on. Now what is there actually here? Is there a direct path to discharge? Because N1 is off. Correct. So there is no way that it can discharge. So now That means it is likely that will not have a output 0. Now what about it? P1 is on, so still there could be charges that is actually going to happen like this, charging. Okay, so now this is again one, there is a charging path. Okay, now what about third condition?
P1 off, sir.
P1 off.
P2
P1
on.
off. Okay, P2 is on.
N1 on.
Okay, N1 on.
N2
N2
off.
off.
N2 is off. Now what is it going to be the output?
1.
It's kind of 1.
It
And
is also
then
charging.
so it is kind of charging. Now what about this case?
P1 is off.
P1 is off.
Okay,
P2 is off.
P2
P2 is
is
off.
off.
okay,
N1 and N2 both are
N1,
on, sir.
N2 on.
N1 and N2 on.
okay. Now when both of them are on, what is it meaning?
Zero
It is
discharging,
like
sir.
There is a discharging
discharge.
path. So that means it is kind
Zero.
of discharging. Okay. So now is it same as what we have this, is that circuit and the truth table, are they matching? Is this Z and this Z, are they same or are they different?
Same, sir.
Same, sir.
Okay, now so this is a kind of formula or the method that I follow. So when you have a bar, so just leave this bar as it is and then take the equation AB and draw the circuit that is kind of in series here. Now the PMOS side, so we when NMOS is in series and your PMOS becomes a parallel. Now you have drawn that parallel circuit and you're done now because this CMOS is inverting by nature. Okay, CMOS is basically inverting in nature. Okay, so now for AND gate, how do you do this? Okay, by the way, now how many transistors are there in NAND?
4.
4.
4.
Okay, so four transistors. Now what about AND?
6.
6.
Okay, so now what is the formula for AND?
AB.
AB. Now what is that we need to do? Converting this into AB bar and then there is one more bar. Correct? So now this is basically NAND and then plus inverter. Agree? NAND plus inverter. So in CMOS, if you ask me, NAND is the basic circuit that we build. Okay, and then when if you want AND gate, you add one extra inverter. So that is how you are actually going to form a AND gate. Now AND gate, how many transistors will be there?
6.
So here there are six transistors. Okay. Now, so what is which is the cell that is having a bigger area?
Under gate.
And
So your AND gate is having a bigger area. Okay. So don't you should always remember this. NAND will have a lesser area, and when you want AND, you need more area. The cell requires, basically the cell will have a six transistors. Okay. So it is this your NAND. Now, if you want to convert that NAND into AND gate, what is that you should do? So this is going to be your Z, which is kind of AB. Now this Z, which is AB whole bar. Okay. Clear? So this is how you actually draw the circuit for a given Boolean equation. Okay, now let's quickly, can we do, okay, so I think let's take a short break, and once we come back, let's try to do it for the NOR and then few other, Boolean equations. So, and then we'll look at how we can, draw layout and etc. Okay, so it is 8 5. So let's assemble at 8:15.